So notice I've got the ones highlighted that I want to be sure and touch. And these are, some of them are unique and there are no duplicates, but a lot of them are duplicates. So that's why we're not going to cover everyone in the document. All right, so let's start with number one. Which of the following is an example of a quantitative observation? Now, I can't for the life of it remember if I had made a distinction between quantitative and qualitative. If I didn't, now's the time. Qualitative observations are those that obviously speak to the quality of something and have no scalar associated with them, like numbers. Right? It's just the solution is blue. That's it. Now, if we stick that solution in a spectrometer and we get a peak absorbance at, say, I don't know, 400 nanometers, that would be a quantitative observation. You'd have a number and a unit associated with it. So that's the difference there. And if we look at our choices, the piece of wood is longer than the metal is longer than the piece of wood. Right? So that's qualitative. Solution 1 is much darker than solution 2. That's qualitative also. Liquid in beaker A is blue. I stole my own thunder there. That's qualitative. Right? So the temperature of the liquid is 60 degrees Celsius. That is quantitative. All right. Here's my eraser. Haven't opened it out yet. And we're going to do 2 also. All right. Generally, observed behavior that can be formulated in. Just a second. Is there anybody that has real problems with any one of these questions that we need to get to? Because I want to be sure and get those before I get too deep into the weeds.
5. I didn't understand it when I had that.
Okay.
Some odd reason I cannot.
All right. Since it's close to the front, I'll just make a note over here and we'll be sure and get to 5.
Okay.
If,
I struggled with the conversions that have 2 units, like pounds per square inch, things like that.
compound units.
Yeah.
Okay. You got an example, Sue?
37 was like one of them.
Okay. And we can do others, you know. Anybody else?
There's another one on here, but I'm trying to see which one it was.
Okay, when you find it, let me know.
Oh.
All right, so we'll carry on. A behavior, an observed behavior that can be formulated into a statement. Let's see, it's not covered up for you, but it is for me. Sometimes mathematical in nature is called what? The key term here is the presence or absence of why. This says nothing about why, does it? That means it's a law. If we try to explain why, or if we try to insert a model of some kind, now we're talking about a theory. So this would be a natural law. That also brings up another point. If the answer you come up with doesn't match exactly one that's in the selection, pick the best one. Okay. That eliminates a lot of anxiety and problems down the road. Okay. Oh, okay. There's 5. All right. Order the 4 metric prefixes from smallest to largest. That is the size of the unit. Let's see. What do we have to choose from here? We got nano. Let's see. We got milli, centi, and kilo. Milli, centi, kilo. Let's see if we've got any different ones. Milli, nano, centi. Okay. Okay, that's it. That's all the ones we have. So these prefixes, how do they modify the base unit? Right? Nano is times 10 to the minus 9. Right? It's a billion. Milli is times 10 to the minus 3. Centi is times 10 to the minus 1. And kilo is times 10 to the third. So if we're going from smallest to largest, we want the smallest. Here's the smallest, 10 to the minus 9. So this is the first one. Second one would be this one. Yeah, they're in order. So I guess A is the answer. Okay, does that answer your question? Does it make any sense? Wasn't five, it was five was a problem, wasn't it?
Yes,
Okay,
yeah.
yeah. Sometimes, at least in the beginning, chemistry requires a good bit of memorization. You got to learn the language first. Once you got the language down, then you can start synthesizing problem solutions. Right? But in the beginning, you just got to memorize some stuff. Okay, I think that may be the source of the problem here. What do they mean? So the unit that this is attached to, it depends on what the base unit is. If it was nanometers, this would be equal to 10 to the minus 9th meters. Okay, one of these is a billionth of a meter. That's what the nano means. Okay, and the way I look at it, if you see this equivalence like that, then you see this right here, this right here are equal. Nano and 10 to the minus 9. And this one stays the same. To differentiate. Okay, well, I'll come back to that when we start doing dimensional analysis. When we're unit conversions, sometimes unit conversions can be best if you focus on the prefix. And I'll point that out when we get to it. There's another one of that type that you need to deal with. I don't see one right now. If I scroll past one that's of that type, then I'll stop and we'll do another one. Okay, 6 and 7. 6. Okay. 8.1 kilograms contains how many grams? 8.1 kilograms is where we're starting, and we want to end up with grams. So we need, it was in the wrong place. We need something that will converge between the two. Right? We need a unit, a conversion unit. Right? So your destination is grams. It needs to be in the numerator. If we've got a conversion factor if a single conversion factor, then all you need is to put this value in the numerator, this value in the denominator, because that cancels. This is in the numerator. That's in the denominator. So when we multiply them, we do the same thing to the units that we do to the numbers. We multiply them together, all right? So kilograms times 1 over kilogram cancels out. Okay? So we cancel that out and that. But we need the numbers that associate the two, right? How many grams in a kilogram? What does K mean? 1,000. Right. So there's the K right there. Okay, so 1,000 times 8.1 is, let's see. Yeah, it's in scientific notation. So it'd be 8.1 times 10 to the third. That's what 1,000 is, 10 to the third grams. Okay. That's the dead silence. Am I losing you? Or everybody okay? Okay. This is fundamental stuff. I mean, if this stumps you, then the rest of the semester is going to be a nightmare. How about 7? Got to scroll a little bit. There we go. Convert 0.3980. 80 points. Meters to millimeters. Okay. Usually, if you're in in the same system, if you're in, especially if you're in the metric system, if you're converting one metric unit to another one, you can usually do it with one conversion factor. So we need meters on the bottom, cancel that out, millimeters on the top, because that's what we want. So now we just need the relationship. Now you can do it either way. You can say 1,000 millimeters in a meter, or you can say that milli means 10 to the minus 3, doesn't it? 10 to the minus 3 meters. But dividing by 10 to the minus 3 is the same thing as multiplying by 10 to the third. Remember that one? Right. When you take the inverse of something, for instance, when we get the gases, we may want to do a conversion. We may want to take volume and take the inverse of it. So volume's in liters, correct? That's the fundamental unit. And if we take the inverse of that, the units are the same. So it becomes 1 over V, and the unit becomes liters to the minus 1. Remember, the inverse of anything is to the minus 1 power. Right? Okay. We'll come back to that one in chapter 5. Okay, but now, what's 1,000 times that? Well, let's see, what do our answers look like? We've got a mix of standard notation and scientific notation. So let's see, what would the standard notation be? We move the decimal place 1, 2, 3, correct? 398.0 millimeters. See, is that one up there? Yep, that's A. Okay. All right. Number 9. I have to put it down there a little bit so I can see it, because I've got a sidebar here that sticks in the way. Number 9. What's the measure of resistance an object has to a change in its state of motion? We didn't put it in exactly those terms. Maybe your book did. But a resistance to a change in motion refers to Newton's first law. And it refers to mass. Right? Something at rest doesn't want to move. Something that moves doesn't want to stop unless you force it. And that's due to their mass. So we got another A. Right. Let's see. How about number 11? When I might have to shrink this one right here so I can see see things. 11. All right. This one can be a little tricky because we're dealing with real numbers here. And we're dealing with a notation that we hadn't been introduced to yet, the plus or minus. All right. Has anybody had statistics? Okay, so you know what plus or minus means. It's an expression of range. The number is uncertain, very uncertain, so to speak, outside that range. But inside the range, we have a more confidence in the value. So when we say something like 1.201 plus or minus 0.001, where's the uncertainty expression there? Remember, these are the certain numbers here. This is the uncertain digit. So the plus or minus is expressing uncertainty for that value. So it could be let's see, plus or minus 0.001. It could be 0.202, or it could be as far as 200. Right, plus or minus 1 from that value. Okay, that's what that means.
I got that one.
Okay, so each one of them has the same uncertainty. And we're looking at 0.201, 0.202, 0.200. And all three of those values are in range of this one and its uncertainty. So they're grouped pretty close together. So the question is, which one is it? Is it both accurate and precise? Or is it one or the other, or none?
Both inaccurate and precise, or imprecise. For some
Oh, okay. So Yeah, it is precise. It's grouped very well, but the accepted value is 1.000.
Okay.
Right? It's nowhere near that. That's why it's not accurate. It's not accurate, but precise. Okay. All right. And that would be what?
See.
C, yeah, precise but inaccurate. Let's see, where were we? 11. Okay, we're going to look at these targets. And we're trying to find out for questions 12 through 13, which of the following figures represents a result having high precision, that is, very tight grouping. Okay. Looks like Roman numeral 3. Well, Roman numeral 3 has good precision. Who else has 2 has good grouping too, doesn't it? Okay. So 2 and 3, because 1 is way off mark. 2 and 3 would be E. Okay, so 12 is E. Let's see, we got 13 to look at also. 13, which of the following concerning these figures is correct? We're looking at, okay. I may have sort of alluded to types of error. Oops. 13. When we talk about systematic versus random error, types of error. Think of it this way. Systematic error is an error that we can get a handle on. And it happens the same way every time, so we can correct for it. It's kind of like our bullseye, and we have tight grouping up here, and they're always about that same distance away from the bullseye. So you can correct for it, like you can dope your scope to bring all those back down there. That's systematic error. Random error, there's no way to tell. It's all over the place. Yeah. The only way you can get a handle on random error is to replicate your measurements as many times as necessary. And that's what researchers do. Right? If you've got I think I mentioned my field research. I had 5 years of field research for my PhD. And you have to have that much because environmental conditions out there in the field are just all over the place. So in order to get reliable data, you've got to replicate your crops 5 or more seasons. Okay, so that's the difference between systematic and random error. Systematic, I think, is usually very tightly grouped. It's got good precision. Random error is all over the place. It could be both imprecise and inaccurate. So let's see, which of the following statements concerning these figures is correct? Figure 1 represents systematic error and figure 2 represents random. Okay, let me go back up. Right. 1 is random, 2 is systematic, I do believe. All right, so that's backwards. A is backwards. 1 is not systematic, 2 is systematic. So let's see, do we have one that goes the other direction? Yeah, B. Number 1 represents random error, right? Those shots are all over the place. And 2 is systematic because they're very tightly grouped. And all we have to do is make a correction for position, and you can bring them all back down to the bullseye. Okay, that's the difference. All right, so let's see, we're moving on to number 16 and 17. Okay. 15. The amount of uncertainty in a measured quantity is determined by, okay, we didn't spend a lot of time on this either, right? When you're making a measurement, you're human, right? You're in control of the measurement, but usually you have a tool, right? So there are two sources of error there. There's the human source, and there's the source of your instrument. How accurate is your instrument? How precise is your instrument? So you've got those two sources of error. And what certified labs usually do is when they have a sample come through from the certifying agency, they will have several lab techs analyze that same sample. And that gives them a spread of values. Now the instrument itself, well, actually, you can kill two birds with one stone. You can have the techs, two or more techs, analyze the same sample multiple times. Right, then you can get a handle on how accurate is the instrument and how accurate are the techs. So it depends on both the observer or the person that's doing the measuring and the measuring instrument. Both of those are limitations to the uncertainty in your measurement. I think I mentioned earlier, the periodic table has 118 elements on it, and there's some of them that were man-made. But now we're discovering some of them are out in nature because our instrument accuracy is improving. Right? We couldn't detect them earlier. I mean, we had to make them. But now that we've identified them and we go looking for them with more modern instruments, you can find them out there in nature. Okay, 17. And of course, the better the instrumentation, the more it costs, right? And very often, the more training your tech needs to use it. That's another issue. A scientist obtains the number 0.045006700. Okay. So what's the question? If this number actually has 4 significant figures, how should it be written? Okay. We got all 3 types of zeros here. Right? Which ones matter and which ones don't? Okay. These are not significant. Right? They don't count. Those 2 are significant and these 2 are significant. Right? But we can only keep 4 significant figures. So when you're judging which ones to keep, you start with the first significant figure to the far left, which would be 4, and you count 1, 2, 3, 4. So we've got to limit it to these 4. That means we have to look to the right of this one and say, what is that? 5 or greater? Yeah. So we have 0.04501. Okay. Who's next? 20 and 2021. Get both of them on there. Am I wasting your time with some of these? Okay. Because if everybody's got a firm grasp of some of these, just tell me and we'll move on. Right? Time is precious. Express this number in scientific notation. 0810. 0810 in scientific notation. So we need something times 10 to a power. If we move to the right, we're storing up negative values of 10. And so if we come over 2, that's -2, and we're left with 8.10. This only has 3 significant figures. That only has 3. Okay. Now, to check yourself, which is a good habit to get into, right? Does that make sense? That's a small number. Is this a small number? Yeah. And some people make a mistake and go the other direction, 1, 2. Well, that'd be kind of hard to do with this one because what are you going to do with those zeros sticking out there in front, right? Bad example. 21. So we're going to do express this number in common decimal form. All right, so we're going to go backwards. 6.49 is it? Times 10 to the minus 3. Okay. This needs to be a small number, so which way does the decimal move?
To the left.
Yep, go to the left. 3 places. So let's just put a bunch of zeros out here to pick up the slack. 6, 4, 9. And we're starting here, so we go 1, 2, 3, right there. And we can get rid of these 2. And that. So 0.00649, and we got the same number of significant figures in both. And A is the answer. Okay. Right. Let's see. Yeah, get those 2 on there. 22. Express the number in common decimal form. Oh, so now we got one that's going the other direction. 2.37 times 10 to the 4th. And so we need a number that's big. That means the decimal needs to move to the right. Okay, 2, 3, 7. Put a bunch of zeros out here. 4 places. So we go 1, 2, 3, 4 here. Now, we can't leave that decimal there, can we? Because we only need 3 significant figures. So we have to get rid of the decimal, and that agrees with those 3. Okay. 23. We generally report a measurement by recording all the certain digits plus how many uncertain digits? 1, right? 23 is 1 uncertain digit. And every scientist knows that. When they see your data, a value that you're reporting, they're going to look at that number and say, the farthest one to the right is uncertain. The rest of them are certain. Right. Does this look familiar? At least, how far did you go before you departed? Did you get into chapter 3 and 4?
I think I did that before you read.
Okay, I'm just curious. Okay, so all of this will look familiar, and we'll get into some new stuff for you in chapter 3. 24. All right. You're asked to determine the perimeter of the cover of your textbook. Okay, so the textbook would be something like this. And what are the values? Drawing pictures helps me. You measure the length is 39.36 centimeters. Right? 39.36 centimeters. Right? And 24.83 centimeters up here. Say 83. Yeah, 83 centimeters. All right. How many significant figures should you report for the perimeter? So what's the perimeter going to be? It's going to be 39.36 again. Right? Got that on that side, both sides. And then the other one, 4.83. 3. Yeah. Add them together. So for this one, use the add subtract significance rules. Right? We line up the decimals and then we just add them together. Right? 3 6 is 18. Right? Carry the 1. We got 6 and 16 is 22 plus 1 is 23. 2. We got 18 and 8 is 27. 28, 29. And 2, 4, 6, and 6 is 12. Correct? I think. All right. So we've got values here. These uncertain values here line up with that one. So we can keep all of them. That means we have 5 significant figures in the answer. And we started out with only 4 for each of the values. Let's see. 24. Yeah, E, 5. 5 significant figures. The most often students make the mistake of applying the add, subtract, applying multiply, divide rules to everything. Add, subtract also. And that'll get you in trouble, especially when you have compound calculations that incorporate both rules. All right. Moving on. Oh, 25. I didn't just do that. No. Consider the numbers 23.68 and 4.12. The sum of these numbers has so many significant figures, and the product of these has so many. All right, so we're going to do it both ways. 2368, 412. 2368, 412. Let's do the add subtract first. Know what it says? Sum, yeah. So that's 0, 7, 8, and 7, and 2. Right? We can keep everything. That's 4 for the sum, and then for the multiplying, we don't even have to do the answer. We just need to look. If we're going to do multiply, we say 3 limits the answer. So it's 4 and 3. 4 for the add subtract, and 3 for the multiply. Okay. That would be D. Okay, but we're going to take these two numbers and do different calculations. One calculation is add them together. So when you add them together, we line up the decimals and we keep the last digit is the uncertain one. So we get to keep all these right here, the left. And that gives us 4 significant figures in our addition, our summation. But when you multiply them, then the multiply rule says we're limited in our answer to the last one, to 3 significant figures. Now, it's not going to be that value, right? Because 4 times 23 is in the neighborhood of 100. Right? But we can only keep 3 significant figures in the answer because it's a different rule. Okay. So it's 4 and 3. Let's scroll. 27. Using the rules of significant figures, calculate the following. Okay, this is subtract. I guess the idea here is to see if you know that the rule applies to subtraction as well as addition. 179, 0.179. We've lined up our decimal points. We're going to subtract. So understood 0 here would bring down a 1. 9 from 12 is 3. 7 from 9 is 2. 1 from 9 is 8. And that leaves us with 3 here. So we have to chop it off right here, because this is the uncertain digit for this operation. And that means this is 1, so that one stays 3. We get to keep just as is. 3.823, which is 8. All right. And my goodness, I'm already running out of time. It's a good thing we have a lab today. What's the best answer to report for this operation? 32. Now we've got a hornet's nest calculation. 3.478 times, 1.164 grams. And they're giving us units. And this is divided by 2.00 milliliters minus 1.69 grams per milliliter. Okay, we do have parentheses in here. So we're going to do parentheses first, and then no exponent. Multiply, we took care with parentheses, and then divide, and then we subtract. So we can do this whole operation right here before we get to the add subtract rule. All right. I don't trust myself to do that one in my head. So let's see what the, we have to apply the significant figures rule to this operation first before we can go that far. So we may have to do some rounding here. 3.478 times 1.164, and then divide by 2. So my calculator tells me that this is 2.024196. We got 4 here, 4 there, and only 3 here. So we've got, that's a 4. So we're going to round off to 2.02. Okay. Now we're going to subtract 1.69. Okay, line up the decimal points. I can do this with my head. 3. That's it. Correct? Because I borrowed from that one makes it 1. So the answer here is 0.33, and it's only got 2 significant figures. What did I do wrong? I did something wrong.
On the graph, 1.69, it says 0.169. You wrote the phone.
Oh, wrote it wrong. Thank you. 0.169. Okay. We're good up to that point. Minus 0.169. All right, let's try this again. 9 from 0 is 1. 6 from 11 is 5. 1 from 9 is 8. 0.851. But we have to chop it off right there. 0.85. There we go. No, I did something wrong. Oh, I needed to keep a 1, didn't I? I only borrowed 1 from that. I didn't borrow the whole thing. 1.85. We'll get there eventually. Boy, would I bomb my own test? Okay. 32. 35. Express the volume 781.2 cubic centimeters in liters. 35. We're getting there. We're almost at 37. 781.3 cubic centimeters, and we want liters. Right? The liters is always capital. Okay. This is a volume, and this is a volume. So what's the relationship here? Well, if it helps, we can go ahead, we can either use a conversion, or we can say, we know that cubic centimeters is milliliters. That's an equivalence. If we know that's milliliters, now all we need is to say milliliters in the denominator, that's in the numerator, and liters in the numerator here. So what's the relationship here? How many milliliters in a liter? 1,000. So if we divide that by 1,000, or we could say it this way. 10 to the minus 3 liters is 1 milliliter. Either way, it works. Milliliters cancel, and then we multiply 781.3 times 10 to the minus 3rd. Now all we have to do is convert to scientific notation. No, we don't. It's in standard notation, right? So we need standard notation. If we incorporate this 1,000th into that, which way does the decimal move? Yeah, it has to move to the left because the resulting number needs to be small. So if we move it 3 places over, 0.7813 should be liters.
There should be 2.
Should be a 2. Having trouble today. I was thinking ahead. I bet I picked up the 3 from there. No, I picked up the 3 from here. That's what I did. Okay. Yeah, that agrees with the answer sheet. Well, at least you guys are telling me. I've had classes that just let me go right on to the bitter end and never say a word. And maybe I catch my own error, and maybe I don't. Okay, 37. The pressure of Earth's atmosphere at sea level is 14.7 pounds per square inch. 14.7 pounds per square inch. Okay. What's the pressure when expressed in grams per square meter? So we're headed for grams per square meter. All right. When you have a compound unit of measure like this one, pounds per square inch, convert one at a time. So this is a measure of, well, this is actually a measure of weight, but we're going to treat it like mass because the conversion factor goes from pounds to grams. We're going to do that one first. We need to get pounds into the metric system. So what's our equivalence? We're given some information here. 2.205 pounds per kilogram. So if we have kilograms here, and we put pounds on the bottom, right? Because we want to cancel pounds. And so it's 2.205, 2.205, 2.205 pounds per kilogram. That gets rid of pounds. Now we're in the metric system and we can convert to grams. Kilograms, grams, 1,000 grams in a kilogram. Okay, that gets rid of kilograms. Now we can work on square inches. We want to get to the metric system from square inches. So, yeah.
This is where I go.
Okay.
So you don't have to restart the number into inches. Like you can take whatever number that you've converted into grams, use the number that you have up until that point.
Oh yeah. Mm-hmm.
Okay.
It's a chained conversion.
Okay.
Yeah, we just chain them all together.
I did 2 totally different things.
Okay. I see where that would be the problem.
Oh yeah.
Okay, the conversion factor we're given is inches to centimeters. Right, so inches goes where? Up here? Because that's in the denominator, this needs to be in the numerator. And we got 2.54 centimeters per inch. All right, where's the problem? Yeah, that's squared and this is not. So all you have to do to get the squared conversion is to square the whole thing. Right, because you're going to do to the units and to the number. So you're going to square this one. 1 square inch is 2.54 squared square centimeters. Okay. Everything you do to the number, you do to the units. So that'll give us square centimeters. Need some more room here. All right. So we got square inches. There we go. There and there. As long as we don't forget to square. Now we've got square centimeters, and we need to change centimeters to, see, I forgot where I was going now. Grams per cubic meter, grams per square meter. Grams per square meter. There we go. So how many centimeters in a meter? 100, right? But that one needs to be squared too, doesn't it? Because you got to have a square down here. So we'll square this one. And this square centimeters will cancel that square centimeters. But we got to remember, we got to be sure and square that when we do our calculations. Question?
I don't know how to ask. So usually whenever you need to get to the final unit.
So the answer is B, 1.03 times 10 to the 7th grams per square meter. Yep. Okay. Lost my remote people. Hopefully they'll come back on once they figure out I'm not there anymore. 41. The density of liquid mercury is 13.6 grams per milliliter. 6 grams per milliliter equals density. Okay, what's the density in units of pounds per cubic inch? Well, this is similar to the last one. So which one you want to convert first? I like to do the top one first. Want to go to pounds, right? Are we given? Yeah, pounds per kilogram will get us into the metric system. So, well, actually, we can't use pounds per kilogram because this is grams. So we got to convert this to kilograms first. Then we can use that conversion factor. Well, you can do it this way, right? How am I going to get to where I'm going? Pounds per kilogram, 2.205 per kilogram, 1,000 grams in a kilogram. Right? So we cancel the grams, we cancel the kilograms, we got that. Okay, we're good for the numerator. Now we need the denominator. We need milliliters up here to do what? Inches. Yeah. That's good. Convert milliliters to cubic centimeters, right? Yeah, because we're going to cubic inches. So cubic centimeters, that's 1 to 1. Okay. Now we need inches and centimeters. 2.54 centimeters per inch, and we need to cube it. Okay, now we get rid of centimeters, leaves with cubic inches, pounds per cubic inch. And in the interest of time, our answer should be 4.91 times 10 to the minus 1. Pounds per cubic inch. Okay. I wasted too much of your time. I need to move on. Okay. During a physics experiment, 46. During the physics experiment, an electron is accelerated to 93% of the speed of light. What's the speed of the electron in miles per hour? Okay. So where are we starting? We want to convert the speed of light from what? Meters per second. Speed of light is 3 times 10 to the 8. That's to 3 significant figures. That's okay. Times 10 to the 8 meters per second. But we're only 93% of the way there. So what's our multiplier? What does 93% mean in decimal terms? 0.93, yes. That's where we're starting, 0.93 times this. Now we need to convert to miles per hour. Okay, so meters to miles. Our conversion factor is kilometers to miles. So we need kilometers, there they are. 10 to the third meters per kilometer, gets rid of meters. Now we can convert kilometers to miles. Like kilometer, 1 kilometer is 0.6214 miles. Kilometers gone. Now we convert seconds. Seconds to hours. How many seconds in an hour?
60. Well,
That's in a minute.
it's in a minute.
Now you can chain them, right? You can just do like this, right? Seconds we want to get rid of, and minutes, and then you can convert minutes to hours. You can do it like that, right? 60 seconds, 60 minutes in an hour. Do it like that. But if you do it once or twice, you know that there are 3,600 seconds in an hour. Yeah. So that gets rid of, there's miles, we got that. Now we're getting rid of seconds, minutes. There we go. So now that's the thinking part. All you have to do is crunch the numbers from there. And it should give you 6.2 times 10 to the 8th. Actually, should have 3 significant figures there. Right? So this is a case where you pick the best answer. Right? If I had time, I'd go ahead and do the calculation, but that has no bearing on the rest of it. It's just this one, 3 significant figures. Right, 93% is an exact number. These are all exact numbers. So it should be 6 point something that was rounded to 2. 10 to the 8th miles per hour. It must be, the authors of this question must be assuming that it limits the answer. I would, but maybe they do. Okay, 46. 49. In 1928, 29.3 grams of the new element was isolated from 660 kilograms of the ore molybdenite. Well, there's a date giveaway. That element is probably molybdenum. 29.3 grams were isolated from 660 kilograms. 660 kilogram sample. And this is element X. Okay. The percent by mass of this element in the ore was. Okay, we're looking for percent by mass. Did we do this? Did we do a percent by mass? I don't remember that we did. Okay, percent by mass. All it is parts per 100. So if by mass, it'll be mass per mass, grams per 100 grams. Right? So the units have to agree. This says kilograms. So this has to be converted to grams. Right? How many grams is 660 kilograms? Times 1,000, right? Right? That's what the kilo means. That thing. So that's 6.6, and that 0 is not significant. Right? There's no decimal there. 6.6 times 10 to the 2 more. So 10 to the 5th, right? You add the exponents. So this is the mass of the sample. This is the mass of the element, 29.3 grams times 100. Okay, it's going to be a really small percentage. And we're limited by 2 significant figures here because there are only 2 there. And if we did the calculations, we had time to do it, it'd be this percent. Okay, really small amount. Molybdenum is an essential element. Not for us. It's essential for plants. Okay. 50 and 51. I know we did this one. Temperature conversions. All right. 409 Kelvin equals what? 409 K. We got centigrade and Fahrenheit. Well, in order to get Fahrenheit, you're going to have to go through centigrade. So we might as well convert it to centigrade, Celsius, pardon me. Convert to Celsius, and if the answer is not there in Celsius, we'll go on to Fahrenheit and find the answer. So remember the formula? K equals C plus 273. So C would then be what? C equals K minus 273. So we'll subtract 273 from this and get 6, 3, 1, 136. Yes, Celsius. Right. Is that up there? Yeah, there it is. So test taking technique, you found the answer. Mark it down and move on. Okay. Oh, okay. Yeah, I've got, do you need any of the hard copies from last week? I got a whole stack of them here if you want.
Okay.
Somewhere. What did I do with them? Use them for myself. Oh, the only difference is that the crossword puzzles are wrong. Let me see. Crossword. You may have already figured that.
I promised there when it dropped out.
You know what? I forgot to plug it in and the battery went dead. Good. It started from the other end. No, it's not me. Okay, well, that's good. Now, take those.
Okay.
And the crossword puzzle extra credits are over on the bench. I mean, on that black and gray thing. And then the other one that you need is in the upper right-hand corner of that stack. That's the lab for next week. Okay. The lab for this week is in that stack. Okay. Let's see. 51. We're in the review document, chapter 1. I haven't even got out chapter 1 yet. I'm out of time for the lecture. So we're bleeding over into lab time. Melting point of a certain element is 391 C. 391 degrees C. What's this Fahrenheit? What is this on the Fahrenheit scale? So you need a formula for Fahrenheit. Right? This is the way I memorized it. 9/5 C plus 32. So all you have to do is plug in the numbers the way it is. 391 plus 32. All right, so here's a good place where you can do estimation and see if the answer comes even close to what you think it should be. All right, what's 9/5 of 3.91? Well, it's almost 2, but not quite. All right, so 2 times 350 would be 700, it's like 770, 780. So it'd be a little over 400, right? No, I'm wrong. 1.8, oh, no. 2 times 400 would be 800. So it's like 750, it's like 780, 800, something like that. These are the closest one, I think. Yeah. So you work it out, right? That's, of course, you want to do that on a test, but I'm in a hurry. But if you do an estimate like that, then you can see if your answer makes sense, right? Maybe your finger slipped on the calculator and you get the wrong button. You hit add instead of subtract, or subtract instead of add, or multiply and divide. And if you do an estimation in your head, you can come in the ballpark and see if your answer makes sense. Right. Let's see. 54. In 1984, which is blue smoke. They don't care what year it was, right? That's word problem for you. Word problems are designed to confuse. Right? I'll keep that in the back of your mind. Some drums of uranium hexafluoride were lost in the English Channel, which is known for its cold water at about 17 degrees C, at the bottom of the English Channel. The melting point of uranium hexafluoride is 148 Fahrenheit. 48 degrees Fahrenheit equals the melting point of uranium. That's not the way to write it. Temperature, melting point. In what physical state is the uranium hexafluoride in these drums? Well, if you're in a hurry, you can be pretty sure if you know anything about metal fluorides, it's going to be a solid. Right? Now, if you're in a hurry, that's the way to go. But if you need to prove it, you need to convert this to Fahrenheit and compare it to this value. Right, so how would you do that? Well, Fahrenheit equals 9/5 or 1.8 times 17 plus 32. And you can probably do this one in your head. Right, what's 2 times 17 would be 34, but it's not quite 2, so maybe it's 30. Plus 30 is 64 or 65 degrees Fahrenheit. Right. So it's not warm enough. It's too cold. It's going to be a solid. This is the temperature at the bottom of the channel. This is its melting point, which is actually, well, all right, uranium, yeah. That's why uranium is converted to hexafluoride anyway, because it lowers its melting point. And during World War II, when we were trying to separate uranium 235, which is the fissionable material, from uranium 238, which is the not, this is only about 0.5%. Right, so you need to separate them. Trouble is, pure metal, that's a massive, it's very high melting point. And then you have to get it into a gas phase too. Right, so in order to do the separation, they convert it to the hexafluoride. And that has a much lower melting point. You can get it into the gaseous state. Beyond that, it's a little more, and you make a gas out of it. Then you can separate the two by one of a couple of different methods. Right, that we don't have time for right now. But the metal would have a melting point that's like 10 times that. The real trick was to find a material that wouldn't corrode with the fluoride, because metallic fluorides are very corrosive. So along came Teflon. Saved the day. Let's see. From DuPont Corporation. 56. A monolayer containing 3.23 times 10 to the minus 6 grams. 3.23 times 10 to the minus 6 grams is the mass of the material of oleic acid. And we take this oleic acid and drop it on water. And it says has an area of 20 square centimeters. Right? So you got, looking at it from the top, right? You drop the oleic acid here and it spreads out into a single molecule thick layer. How do you know? How can you tell the diameter? Because, all right, oleic acid is about the same optical density as water, maybe a little bit different, but it's going to be difficult to find the edges. How do you find the edges of your circle when you drop it on there and it spreads? Just blow a little talcum powder on it, right? You drop it and it'll go like that. You can see the edges. Measure the circle. So the total area is 20.0 square centimeters. All right. The density of oleic acid is 0.0895 grams per milliliter. What's the thickness of the monolayer? That is the length of the oleic acid molecule. Now, this doesn't tell you that, but oleic acid is a fatty acid, right? If you've had, anybody had anatomy and physiology in here? Oh, okay. Well, uh, true fats are combinations of glycerol and fatty acids. And you break them apart. If you break them apart with sodium hydroxide, you make soap. Okay. Anyway, the fatty acid has a polar end on it and a nonpolar chain. Right, so the nonpolar chain is going to be hydrophobic. It's going to be away from the water. And the acid end of it is going to be dissolved in the water. It's going to be right there. So it's going to stand up on its head and its tail in the air. That's how we know that the thickness of that layer is the length of the molecule. Okay, so where are we going from here? We want to find the length of the molecule, right? At the length of the molecule, we have to take this and go like that. It has to be like 3 dimensions like this. Looking on edge. So the molecule is going to be, see, this way. It's going to have the head there, and then its tail like that. So you're actually looking at a cylinder, a very short cylinder with a big area. So what's the volume of a cylinder? If we're going to find out the length of this molecule, we know the area. If we can find the volume, then we can use the formula for volume to find the length of that molecule, right? The volume of a cylinder is the height times the area, right? And that's what we're after right there. We know the area, right? It's 20 square centimeters. What we need is the volume, then we can find the height. So how do we find the volume? Well, we know that the mass of that oleic acid is this, and the density is this. So density equals mass times volume, right? We want the volume. So that's over here and density over there, and mass like that. So we say the mass is 3.23 times 10 to the minus 6 grams divided by the density, 0.0895 grams per milliliter. Let's see, is that right? Yeah, the grams will cancel, right? And remember, in mathematics, the denominator of the denominator is the numerator. So these cancel. That's the denominator, numerator. This one becomes the numerator. Right? So if we do a quick calculation, 3.23 exponent minus 6, and then divide by 0.0895, we get 3.6089 times 10 to the minus 5 milliliters. Now here's a case where if all of your calculations are going to be multiply divide, and we know they are, then hang on to all your decimal points. Don't round it yet. Right? I think I mentioned that. If you round here and then you put in a calculation and round again, if they all rounding up, you've introduced a significant rounding error. Or if they all round down, same thing. So keep all your decimals if you know that there's no add subtracts in there. And then at the end, we'll round to 3 places, 3 places, 3 places. Okay, 3 significant figures. Okay, so now we have the volume is yeah, that's right, milliliters. But this is in centimeters. Okay. So we just say, okay, we know that that's also cubic centimeters because 1 milliliter is a cubic centimeter. So if we put that in here, let's go ahead and solve for this, right? What would that be? H equals volume divided by area, correct? So we've got area is 20.0 square centimeters, and volume is 3.6089 times 10 to the minus 5 cubic centimeters. Right? So 2 of these are going to cancel 2 of those and leave us with a centimeter. So our units are going to be in centimeters. Let's see. Let's divide this by 20, it's still in my calculator. So the height is 1.80447 times 10 to the minus 6 centimeters. Now, what are our answers in? They're in centimeters. That's good. So we round to 3. 1.80 times 10 to the minus 6 centimeters. I hope that was up there.
Yes.
Minus 7? Where did I do wrong?
That's what I got too when I didn't.
You got this one?
Yeah, -6 instead of -7.
Okay, let me go back. See, did I do this right? 3.23 times 10 to the minus 6. Yep. And 0.0895. No, 0.895. That's it. That's my mistake. So that would increase this from 7. I mean, to carry it on through. Because this is a bigger number. You increase the denominator, you decrease the quotient. Correct. So we decreased it. We increased it by 1 decimal place. We decreased it by the same decimal place. Okay. I hope you guys pay better attention to details than I have been. The devil is in the details, as they say. Okay. The density of gasoline, 57. The density of gasoline is 0.70215. 0.70215. No. There I go again. 25. There we go. Grams per milliliter at 20 degrees Celsius. When gasoline is added to water, oh, this is a question about relative density. Anybody had physics? You know that anything that's less dense than water will float, right? So the bulk density of a human body with full lungs is less than 1. Otherwise, you won't float. And that's probably why women float better than men, because men have more muscle to fat ratio. And fat's less dense than muscle. So there it is. Okay, so it's going to float, right? Because the density of water is 1 gram per milliliter. You're comparing the two densities for water. And that makes the answer A. It'll float. Gasoline is going to float for 2 reasons. One is the density is less, plus gasoline won't mix with water. Gasoline is nonpolar. And we'll talk more detail about that in the future chapter. Polarity. Okay, 58. A piece of zinc with a mass of 12.14 grams, zinc, mass of 12.14 grams. Did I get that right? Yeah. Is submerged in 46.3 cubic centimeters of water. Let's say we have water up here to 46.3 cubic centimeters for milliliters, same thing. In a graduated cylinder, the water level increases to 48. Goes up here to 48.0 cubic centimeters. Once we put the piece of zinc in it. Okay. What's the value of the density? What do you need to know to calculate density? You need to know the mass and the volume of that mass. Right? We know the mass, right? 12.14 grams. How do we get the volume? By difference. Right? If the water was at 46.3, drop the zinc in, it becomes 48. That difference is the volume of the zinc. Okay. You can do that as long as you can drop something in there and tell the volume by difference, as long as the stuff you drop in there doesn't react with water. Right? If you drop a chunk of sodium in there, then all bets are off. Right? It'll react with water, but zinc won't. So you drop that in there and you find the difference. So the volume is 48 minus 46.3. So that's the thinking part. All you have to do now is crunch the numbers and you get 7.1 grams per cubic centimeter. Ooh, that only kept two significant figures. Why is that? That's because when you subtract this one, that's one rule. Ooh. So what we need to do is parentheses, because you have to do this calculation before you can do the total. You can't follow PEMDAS here. If you do, you're all messed up. So if you subtract 46.3 from 48, what do you get? 1.7. Did I write the right numbers? 46.3 and 48. Yeah, 1.7.
Yeah, 1.6.
3 from 10 is 6.
I don't know. I was going 9. Sorry. Yeah.
Okay.
Yeah.
It's contagious.
Yeah.
So that's where you get the two significant figures in your answer, because this one leads to 2. Okay. All right. All right. That's moving on. 62. The boiling of water is a physical change or a chemical change? Physical, right? The identity of the water doesn't change. It just changes phases, right? So it's either A or B. Now the question is, which one? Because the water merely disappears, or the gaseous water is chemically the same as the liquid. That's the better answer. Chemical identity has not changed. B is the answer. I'm not going to write that one up there. Okay. All right. So these, let's do it this way. I've never done it this way before, but let's put, let's see, number 70 is based upon those figures. A, B, C, D, and E. All right. What we're trying to show here is components in these mixtures. Right. And the first one is looking for which best represents a homogeneous mixture of an element and a compound. So the elements are going to be those single figures, right? Circles, squares, colored, whatever. Those are going to be elements. And the compounds are going to be close associations, length. Like C is a small gray circle with a larger white circle. That's a compound. Okay. All right. So the first one we characterize as how far apart are those atoms? So these are two elements. Right? This is a mixture. And based upon how far apart they are, it's probably a gas. Right? It's a mixture of two gases. And if they're gases, then you know they're homogeneous. All gases form homogeneous mixtures, no matter what kind they are. So this is homogeneous. All right, how about B? Well, B appears to have a regular structure, and it's only one type of particle, right? One element. This looks like an elemental solid. It's not a mixture, and it's a solid. C is like A. Those molecules are very far apart. It's probably a gas, but it's not a mixture. This is a molecular, right, gas, not a mixture. And D is disordered, right? It's not a regular arrangement of particles, but there are two types of them. So that is a mixture. But it's a mixture of elements. And they're probably liquids because they have similar compactness to the solid. And so this is a liquid mixture. And is it homogeneous? I don't think so. I see groupings of grays here and groupings of whites there. I think it's heterogeneous, don't you? And E. Okay. This is, let's see, this is a mixture of element, the squares, and compounds. The light and dark circles. So this is a mixture. But are they regularly spaced? They appear to be. Yeah. So this is homogeneous. Homogeneous mixture. I'm not sure what it would be, whether it's a liquid or a gas. I think it's too regular to be. I don't know. Let's look at our choices. All right. Which best represents a homogeneous mixture of an element and a compound? Homogeneous mixture, not that one, gas. Homogeneous mixture. All right, that is an element and a compound. One's an element, the other one's a compound. So E fits the best one for 70. 71. Let's see what 71 wants. Which best represents a gaseous compound? Okay. Yeah, that's the compound. So this is C for 71. And 72, which represents a solid element? B, yes. And I think 73 is based on that one also. Let's see what 73 says. Which represents heterogeneous mixture of two elements. Heterogeneous mixture. B. Yeah, heterogeneous mixture of two elements. Yeah. D. All right, that's why I stopped on this one, because sometimes those figures don't make a whole lot of sense unless you've seen something like that before. 75. The following has a different value on the moon compared to Earth. Okay. How about mass? Is it different? No?
Wait.
Yeah, weight. Weight's different. Time's not different. Moles are not different. Moles are counting numbers. Yeah, it's weight. We're not even out of chapter 1 yet. We gotta be getting close. Which separation technique is based on differences in the volatility of the substances to be separated? Volatility. I think we talked about this one in terms of moonshiners. Distillation. is based upon different volatility of the elements. If you heat up the mash, you're going to drive off the most volatile first. And that the temperature will rise to a certain point and it'll stay there until all of that component's gone. And it'll rise again until the next component's gone. And you'll keep doing that until they're all gone. Or you have nothing that's volatile in there left. Like what's left after you ferment mash, the husks. So distillation is based upon volatility. While we're here, what's filtration based upon? Particle size. Yeah. The filter, right? Some filters will filter out only large particles and let the rest go through. Some of them very, very, very fine pores will retain almost everything. Right? In a hospital setting, you got N95 masks where you got special HEPA type filters, and the spaces between the fibers are so small they'll even catch viruses. Solvent extraction. That's a heavy subject right there. Solvent extraction is based upon differential solubility, like how soluble is the compound in this solvent versus that solvent, and the solvents have to be immiscible in one another. So it separates into one preferential over the other, then you can draw it off and evaporate the solvent and separate them. Paper chromatography is based upon affinity of the compounds with a fixed medium. So paper chromatography was invented with paper, just a slice of paper. And you have to say, this is your starting line, and you take an extract of leaves. This was the original. And you dot them right here. Just put dots there. And then you put it in a closed container, and you fill the container up with solvent up to here, like maybe ethanol, and it starts working its way up through the fibers. And you seal the lid. And some of those compounds have a stronger affinity for the paper than they do for the solvent that's moving. That's called the mobile phase. So if they have a very strong affinity for the paper, they'll kind of lag behind, right? They don't separate into the solvent very often. Sometimes they do and they move up a little bit, but the ones that have a strong affinity for the solvent and a weak affinity for the paper, they'll stay in the solvent most of the time. They'll keep moving. So eventually you'll get maybe a streak up here and a streak up here and a streak up here of different colors. That's why it's called chromatography, which means color writing. So it's based upon, it's a term called adsorption, affinity with the paper. All right, so the answer there is distillation. All right. Well, the first people to attempt to explain why chemical changes occur were, all right, we're in chapter 2. Yay. The first people that tried to explain chemical changes were the Greeks, the ancient Greeks, as a matter of fact. Okay. About 2. The first chemist to perform truly quantitative experiments was Boyle, right? And let's see, 3's coming up. 6 foot 3's. The scientist who discovered the law of conservation of mass and is also called the father of modern chemistry. He's the one that lost his head. Lavoisier, right? In the French Revolution, Lavoisier. And which of the following pairs of compounds can be used to illustrate the law of multiple proportions? Remember that one? The law of definite proportions just says what? No matter where the compound comes from, if you identify this compound and that are the same, wherever they came from, they're going to have the same ratio by mass of elements in the compound. That's John Dalton. This one was from Proust. And in order to do multiple proportions, you need an A element, spread this way, an A element and a B element. And they have to be, if you hold one of them constant, the other one has to increase by whole number multiples. So the first thing you've got to do is look at the pairs. Right? Do you have A and B pairs in both of those on either side of the and? Right? A, no. You got nitrogen, but hydrogen is not the same as H4Cl. Right? So A, throw A out. How about B?
No.
No, that one's wrong too. How about C?
Mm-mm.
No. Okay. How about D? NO and NO2. That looks like a good candidate. Hold this one constant at 1, and this one increases by from 1 to 2. That's a multiple proportions. Now, this is our modern explanation for it, but when the law was developed, they had no idea about this. They just knew masses. And of course, the last one wouldn't fit either. So 4 would have to be D. Seven, a sample of chemical X is found to contain 5 grams of oxygen. 5 grams of oxygen. Let's see, number 7. What do we know? 5 grams of oxygen, 10 grams of carbon, and 20 grams of nitrogen. 20 grams of nitrogen. Okay, that's one sample. The law of definite proportions would predict that a 70-gram sample of chemical X should contain how many grams of carbon? Definite proportions say that, what's the total mass here? Let's do that. 0, 5, 35, 35 grams total. So if we take that compound and go from 35 to 70, what's that going to do to the amount of each one of these? Double it, right? So each one of these should double also. That means if we're looking for the grams of carbon, it should be 20 grams. Everybody see that? We doubled the total mass. Definite proportion says the ratio of masses is going to be the same. So in order to be the same from 35 to 70, double this, you have to double that. This will be 40, this will be 10. So answer is E, 20 grams. Right. 9. Which of the following statements from Dalton's atomic theory is no longer true according to the modern atomic theory? Okay. So elements are made up of tiny particles called atoms. Is that still true? Yep. Sure enough. Atoms are not created or destroyed in chemical reactions. In chemical reactions, that's true. They are not created or destroyed. They're just rearranged. All atoms of a given element are identical. Isotopes. They're not identical. They're similar chemically, but they're not identical. They have different masses. Isotopes. Well, there's our answer C. So D and E must be true. Atoms are indivisible in chemical reactions. In chemical reactions, that's true. All these statements are true according to modern theory. Well, we got 2 false ones, don't we? Okay. So I guess you would be justified in saying E as well as C. And so if something like that happens, and I mark you wrong because you didn't give me the answer I was expecting, call me on it. You can get credit for that one. Hopefully I won't do that, but you never know. The chemist credited for inventing a set of symbols for writing elements and a system for writing the formulas of compounds, and for discovering selenium, silicon, thorium is. Now, we didn't talk about this person, but it should have been in your book. The person responsible is Berzelius. He was a Swedish chemist, and he came up with the symbols, the simple letter 1 and 2 letter symbols for the elements. And that when in a compound, they would be set up so that element X and Y together, maybe you get 2 X's and only 1 Y, to write it that way. Berzelius. Okay, 12. Avogadro's hypothesis states that find the one that's closest to what we recognize as Avogadro's hypothesis. Remember, if you got 2 separate gases in 2 containers, their volumes are equal, temperatures are equal, pressure inside the vessel is equal, then what else is going to be equal? The number of particles inside the vessel, as long as they're gases. Right? The number of molecules, number of atoms, whatever the case may be, is equal inside those vessels under those circumstances. So which one fits best?
Mhm.
Yeah, same temperature, pressure, equal volumes, different gases, and equal number of particles. That's right. Yep, D. And that saved, that right there, saved the chemical industry in Europe in the late 19th century. They were pulling their hair out. All they knew about was mass ratios. So they were doing their chemistry with basically recipes, voodoo science, right? Until Avogadro came along and says, wait a minute, this is how you know the exact weight of each atom in your reaction. Then you can put them together as numbers of atoms and molecules reacting rather than masses. Then they started to figure things out. Well, it wasn't actually Avogadro that did it. It was his student, Cannizzaro. We'll talk about that later. The first scientist to show that atoms emit any negative particles was C. Is that what I said? Somebody say C? No. D. No, not D. It's the other Thomson, JJ. Hey, yeah. JJ Thomson identified the electron. Hey. About 14. Many classic experiments have given us indirect evidence of the nature of the atom. Which of the experiments listed below did not give the results described? Well, let's see. Rutherford's experiment proved the Thomson plum pudding model of the atom to be essentially correct. Oh, no. He sent the plum pudding model to the graveyard with his gold foil experiment. And he proved that the atom was a nuclear structure, very dense center, and the electrons were out here somewhere. So most of the mass was contained in a very dense center. That was Rutherford. Yeah, he disproved the plum pudding model. So A is the answer to 14. 15. The scientist whose alpha particle scattering experiment led him to conclude that nucleus, well, Rutherford, right? Yeah. Okay, 16. Alpha particles being that thin metal foil may what? Okay, now we're still on Rutherford. What can they do? They can pass directly through without changing direction. Yeah. They can be slightly diverted by attraction to electrons or deflection off the nucleus, or they can be reflected by direct contact with the nucleus backwards or at some angle. Yeah, all of them. All of those are possible. Now, the video that we showed treated everything like billiard balls, right? But in fact, that B is true when that positively charged helium nucleus, right? Helium nucleus That's what an alpha particle is. When it passes through the foil, if it doesn't strike the nucleus, it could be deflected by its attraction to the negative, right? It's positives and negatives. So they could change the direction that way. That would be too complicated to deal with in that video. 17. Which of the following statements about atomic structure is false? An atom is mostly empty space. Yeah, I'll agree with that. Right by about 5 orders of magnitude in the diameter. Almost all of the mass of an atom is concentrated in the nucleus. Yep. Protons and neutrons in the nucleus are very tightly packed. Yep. Number of protons and neutrons is always the same in the neutral atom. Wrong. Now, for the lighter atoms, for the lighter elements, and for most of their isotopes, that's true. 1-to-1 ratio. But as they get bigger and bigger, apparently you need more neutrons to hold all those protons together. So you start to see a divergence where the protons go like this and the neutrons go like that. So D is the answer to that. Let's see. Which of the following atomic symbols is incorrect? Incorrect. All right. So what I would do is I would look at the symbol and the atomic number to see if they match. Right. And I don't have a periodic table in here. So I have to work from memory. Carbon does have 6 protons. Right. The atomic number is 6. Chlorine, 17, that's correct. Phosphorus, 15, that's correct. 19 for potassium, yeah. Nitrogen, though, doesn't have 8 protons, it has 7. So we found the one. Doesn't matter what the other one is, we found the wrong one by the number of protons. 21. The element rhenium exists as 2 stable isotopes and 18 unstable isotopes. Rhenium-185 has in its nucleus, okay, we need our periodic table for this. Rhenium-185, this is one that I didn't have to memorize. So we have to look in our periodic table and see what's the atomic number for rhenium. Let's see, I have to look at the back of the review document. Rhenium is a transition metal, so it's going to be down in here somewhere. 75? Yeah, 75. Okay. So this needs to be 75. And the number of, so it's either A, B, or D. We have to subtract 75 from 185, which is 0, 1, 1. 110 neutrons. So it'd be D. D should be the answer. Protons subtracted from mass number equals neutrons. One. 22. Which among the following represents a set of isotopes? So what do we need to be sure to have a set of isotopes? Well, we're gonna look for isotopes, and Roman numeral would be which ones combine to give you a set of isotopes. First thing you need for isotopes is for all the members to have the same atomic number, same number of protons. So if we look at Roman numeral 1 with 20 protons, who else has 20 protons? 4, right? They have the same number of protons, and A1 has 20 neutrons and 4 has 22 neutrons. So that looks kosher. How about the next one? 21 protons. All right. 5. So we have 2 and 5 have the same number of protons and different neutrons, right? Yeah, 19 and 20. Okay. How about Roman numeral 3? We haven't done that yet. Does it have any isotopes in there? No. It's the only one with 22 Oh, it's backwards. Throwing a wrench in the gear. 18 protons, but that's still the same. That's the only one with 18 protons. I almost fooled myself. So 1 and 4 and 2 and 5. D, 1, 4, 2, 5 would be valid sets of isotopes. All right. 28 and 29. 28 wants a species with 12 protons and 10 electrons. 12 protons and 10 electrons would what? It'd give you a charge, wouldn't it? Might it be positive or negative? You have 2 more positives than you do negatives, right? So it'll be 2 plus. So it's got to be A, B, or C. Right? That's the only possibilities. What we need to do is find out where's 12. 12 is probably magnesium, isn't it? Yeah. So this would be magnesium with a 2 plus charge. Now, does that make sense? Oh, Morgan's back. Okay. Yeah, this is an alkaline earth. It's in the second group from the left. And they're all 2 plus charges. Calcium, magnesium, let's see. Beryllium, they're all 2 plus charges. 29. The number of protons, neutrons, and electrons in this potassium ion. Protons. So we have 19 protons, correct? How many neutrons? 20? 19 from 39? How many electrons? We've got 1 extra proton than we do electrons, right? That's how you get it. Right? Remember, you can only change the charge of an atom by adding or subtracting electrons. You can't touch the protons unless you want a different element. So it would be 19, 20, and 18, which is E. Right, okay, you're about to fall asleep. It's a long one. Do we need a break? We still probably got half of this chapter 2 to go. If you're good, I'm good. I keep rolling. 33. Or if you need to get up, yeah, go ahead. It's recorded anyway. Which of the following are incorrectly paired? Oh, okay. Incorrectly paired. Is strontium an alkaline earth metal? We need to look at our periodic table for that. Yeah, it is. Yeah. It's one of the heavier ones. Right. So A is correct. How about tantalum? Is it a transition metal? Yeah. I'll vouch for that one. How about fluorine? Is it a halogen? Yep. And like B. H, is that a noble gas? No, H is hydrogen. He is a noble gas. Right, so D is wrong. Okay. And ruthenium is a transition metal. Yeah, 34. What that was testing was, do you know where the regions are in your table? And who belongs there? So if you find that element in that table, you say, all right, which region is it in? Which of the following incorrectly paired? Phosphorus. Is phosphorus PR? No, PR is promethium. That's not phosphorus. Phosphorus is P, correct? Palladium. Yeah, B is correct. This is incorrect. Well, we found our incorrect one. Platinum is PT, lead is PV, potassium is K. Is everybody progressing on their memorizations? Okay. That's good to know. And 35 and 36. 35, which of the following are incorrectly paired? All right. Copper, is that Cu? Right. Based on the Latin cuprum. Carbon. Yeah, that's C. Cobalt. Yeah. Calcium. That was right. Cesium. No, cesium is CS. Ce is, I don't know if I gave you that one. Cerium. So you know it's wrong anyway because it's not CS. 36. Antimony. That's right. Stilbium. Silicon. Yep. Silver. Argentum. Argon. Yep, that's correct. Astatine. No. Yeah, AT. What's AS? Arsenic. Exactly right. 37. Okay. All the following are characteristics of metal except. All right. Good conductors of heat. Metals. Yeah. Yeah, metals are good conductors of heat. Are they malleable? You can bend them and shape them. Ductile. Ductile is kind of like malleable, only it means you can stretch them into thin wires. Yeah, that's true. They're often lustrous. If you polish them, they are. Tend to gain electrons in chemical reactions. They lose electrons. Metals lose. So E is the bad one there. Let's see, 41. Look down where I can see it. You're given a compound with the formula MCl2. So we've got 2 chlorine atoms and 1 metal of some kind. Okay. You are told that the metal ion has 26 electrons. 26 electrons, okay. What's the identity of the metal? All right. If there's only 1 metal and there are 2 chlorines, a metal, non-metal produce ionic compounds. So what's the charge of chlorine when it's in an ionic compound? It's a halogen, right? So it's -1. That means total of -2 charges, correct? That means the metal has to have what charge? 2 plus, right? To balance it. This is all about balance. So if it's a 2 plus charge and it's got 26 electrons, how many protons does it have? 28 protons. Now we can look it up in the periodic table and find out what the element is. I don't know offhand. You got your periodic table? 28. Nickel. Did somebody say that? Yeah, nickel. Right? And we did nomenclature, didn't we? Naming. I did that after you guys left, I believe. Okay. Nickel. Can it have more than 1 charge? Yes, it can. So that means we have to use type 2. So if we were to name it, it would be nickel 2 chloride. Okay. Type 2 compound. All right. Scroll. I'm not using my magic wand today because it never works with these things. It works on my PowerPoint fine. It just doesn't. I don't know why. 45. How many oxygen atoms are there in 1 formula unit of this compound. Okay. How many oxygens? 2 times 4 is 8. Yeah. Yeah, 8 oxygens. What's this one called? Well, this is a giveaway here. That's a polyatomic ion. And polyatomics combined with this metal means calcium has to be a 2+ because it's an alkaline earth. So that means 3 times 2 is 6+. And we know that phosphate is a 3-. So 2 times 3- is 6-. They're balanced, right? That's good. So we would name this because the metal can only have one charge. We name it with the type 1 convention, calcium phosphate. That's it. Right? Unambiguous, not redundant. But the answer is 8. Okay, 47. I need to scroll again. 47, 48, we get those together. The correct name of FeO. Okay. Remember your decision method. Is it a metal, non-metal? Yes. There's the metal, there's a non-metal. That means it's either a type 1 or a type 2. Right? Can't be a type 3 because those are non-metal nonmetals. So it's now we have to decide, is it a 1 or a 2? Can iron have multiple charges? Yeah, it's a transition metal. And it's not one of those 3, right? The 3 that are fixed charges, cadmium, zinc, and silver. Right? So transition metal is not one of those 3, has multiple charges. We have to decide, since this is a 2-, it's a chalcogen, always a 2-, when combined with a metal. That means this one, only one of them has to be a 2+. So we say iron, 2, oxide. Okay. 48. The correct name of Ca2+. Ca2+. Well, it's calcium. But it's also an ion, isn't it? Calcium ion. Now, why don't we say calcium 2 ion? Because that's the only charge that it's allowed. We don't have to say 2. It's just calcium ion. And we know that it's a 2+. Okay. That's why B was thrown in there to confuse you. Right. It's just calcium ion. 48. 40. No, 50. 51. What's the subscript of barium in the formula for barium sulfate? Okay. Okay, we know we have barium. We know we have sulfate, which is a polyatomic ion. And you can look it up in that table. You find it has a 2- charge. Where's barium? Barium is an alkaline earth, isn't it? Yeah. It's right below strontium. So barium has a 2+. So that's it. Just one barium, one sulfate, and we're balanced. So the subscript of barium in this one is 1. It's understood to be 1. We don't write it in, but it's there. $53. Formula for sodium dihydrogen phosphate. Okay. We know we got sodium in there. What's dihydrogen phosphate? It's a polyatomic ion. Dihydrogen phosphate. Now, the best way to figure this one out, if you don't want to look at the chart, is we know phosphate is the 3- charge. Phosphate by itself. If we add a proton to it, a +1 charge, that neutralizes one of those charges and makes it a 2-. But if we add 2 dihydrogen, 2 pluses neutralize 2 of those and leave us with just the one minus. So this is going to be a -1, this is going to be a +1, that's it. Sodium dihydrogen phosphate. So A would be the formula. Right. 56. All the following are in an aqueous solution, which is correctly named. All right, now we're talking about acids. A, B, C, D, and E. All right, H2SO4. Is that correct? It's got oxygen in it, so we don't say hydro. That's good. So if it's an aqueous solution, we focus on this part, sulfate, and H's become X. So this one is sulfuric acid. We know it's an acid because it's got a hydrogen here. In fact, all of them do. Right. So we're in the acid realm right now. How about H2CO3? Right? No hydro there, right? Because it's got oxygen. What is CO3? It's a polyatomic ion. Carbonate. H become X. So this one is carbonic acid. That would be good. H3PO4. Right? No hydro there. PO4 is phosphate. H become X. Phosphoric acid. That was right? Yep. How about HCN? No oxygen there. So we say hydro. Then the cyanide ion, I becomes it. Hydrocyanic acid. That was wrong. And then HCl is also a hydro, but it's hydro. Chloride becomes ic, chloric acid. Right, that's the only one that's wrong in that bunch. Right, because it doesn't have an oxygen, so we have to start with hydro. By the way, if I wrote this one, what would it be? We'd have to start with hydro, wouldn't we? Hydrosulfuric acid. The name sounds similar to this one, but it's a completely different molecule. 59. We do it all the time. We got 50 minutes left. We still have to talk about graphing. Okay. Yeah, we should do this. All right, complete the following table. So we've got 1, 2, 3, 4, 5. Five. You 1, 2, 3, 4, 5 across. All right, we got symbol here. We got number of protons here, number of neutrons here, number of electrons here, and net charge. Okay, we're given this one, 206 PB, 206 PB, and we're given this one, Mn2 plus. We're given this one at 31 and 52. We're given this one at 38, 75, and 30. We're given this one at 54, And we're giving this one at 3 plus and 2 plus. Okay. So we use a different color for the filling in the blanks. All right. So this is a neutral atom, right? So the charge is 0. Okay. How about the number of protons? Well, we have to look it up. Right? This is a case where you have to go to your periodic table to find some information. Lead is 82. 82 protons. So how many neutrons? 124. Yeah. And how many electrons? It's neutral, so the electrons have to be equal. Exactly the same. How about this one? 31 protons. Let's see what element that is. 31 is gallium. But it has a 3 plus charge. How about the number of electrons? If it has a 3 plus charge, we're deficient by 3 electrons. 28. Okay. How about this one? 52. 52 is along to E, tellurium. Does it have a charge? Yeah, it's got 2 extra electrons. So it's a 2 minus charge. There we go. And this one, manganese. So we look up manganese, and it's 25 protons, atomic number. It's got a 2 plus charge, so it's deficient 2 electrons. Right? That's it. We're filled. Did I lose anybody? Okay. I usually go all black, but occasionally color difference makes sense. All right. This is following along in a similar pattern to that table, so I'm going to skip 62. I think you can do that one. Symbols. Silver is Ag, calcium Ca, iodine I, copper C, and phosphorus P. I think you guys can handle that. You can save time on that one. How about the names for these? Maybe we better stop for this one. Okay. So FeSO4. This can have a multiple charge, which is 2 plus, because this one is 2 minus. So it'd be iron 2 sulfate. It's A, B. So Na, this one might be a little difficult. C2H3O2. If you got more than one element, if you got an oxygen and more than one element, let's see, 2 other non-oxygens, then it's you're probably looking at a polyatomic. And this polyatomic is acetate. So we've got sodium, which makes it a type 1, a polyatomic and a metal with only 1 fixed charge. So it's just sodium acetate. And acetate is the name of that ion. You don't have to change it. Polyatomics go into a compound with the name that they come in with. It doesn't change. Except for acids. I have to qualify that. Acids do change them. But for these types of compounds, no. How about KNO2? What do we got there? We got a polyatomic. What polyatomic is that? Nitrite. And potassium is a fixed charge, so it's a type 1 compound. Potassium nitrite. How about D? CaOH taken twice. That's a dead giveaway there. That has to be a polyatomic. -1 times 2 is -2 calcium. Calcium is fixed. So all we have to do is say calcium hydroxide. That's the name of the polyatomic ion. And then NiCO3. NiCO3. And there's only one of them. This is the carbonate. So that means this has to be a 2+. And this is a type 2 compound. So it's nickel 2 carbonate. Okay. It's 465. I'm going to let you guys go with that one. How about naming these? The first one, aluminum sulfate, is a type 1 compound, right? Because aluminum is a fixed charge at 3+. Ammonium nitrate is 2 polyatomics together. Ammonium, NH4+, and NO3 is nitrate with a -1 charge. This is 168. This one, sodium H. When H comes second, it no longer has a positive charge. We typically have hydrogens are positively charged if they're first, but if they're second, associated with a metal, then this is a -1 and this is a +1. And the hydrogen becomes hydride. It's like chloride, fluoride, oxide, hydride, sodium hydride. K2CR2O7. CR2O7 is dichromate. That's in your table of polyatomic ions. CCl4. Now we're getting into type 3s. Carbon and chlorine are both nonmetals. So you have to just say how many there are based upon the formula. Right? Carbon tetrachloride. Silver and chlorine. Silver is one of those transition metals that is a fixed charge. So it's a type 1 compound. Right? Silver chloride. That's all you have to say. Calcium sulfate. I think we did that one before, didn't we? And HNO2, that's an acid. Now, you could argue that since I don't put the AQ next to it for aqueous, that you would name it by the other convention, right? And without the AQ, you could say hydrogen nitride. But if you put the AQ next to it, take this, and it's nitrous acid. That's what we're looking for. But you could argue in favor of the first one if you wanted. Because technically, I didn't put it in water. Oh, there's another one. Nitrogen and oxygen, they're both nonmetals. It's a type 3 compound. Dinitrogen trioxide. And then SNI2 is tin, which can have multiple charges. Right? It's not a transition metal, but it can still have multiple charges. Tin 2 iodide, because iodine is a -1, you got 2 of them. That one tin atom must be a 2+ charge to balance. Now we got more. S2O3 is thiosulfate. That's one of those polyatomics. Right? Type 1 compound. Iron 3 oxide. Now, when you write that one, iron 3 oxide, let me put the number up here, 77. 77. When you have iron 3 oxide, you know that the charge on the iron is 3+, and the oxygen is 2- because it's calcium. So the way to solve this one is cross multiply. Bring this 2 over here, bring that 3 over there. So we have 3 Fe2O3. Dichlorine heptoxide. Right? Two nonmetals, and we say how many there are. So Cl2O7 is correct. Cobalt 2 chloride, that's a no-brainer. Aluminum is a type 1, just like it was before. Aluminum is a 3+. Hydroxide is a -1. It's a polyatomic. Sulfurous acid, right? Sulfuric acid is SO4. Sulfurous is from the sulfite, SO3. Okay. Nitric acid, HNO3. Now, I didn't put the aqueous in here, probably should have, but as far as the formula goes, that's correct. Phosphoric acid, we've named that one before. Acetic acid, C2H3O2 is acetate. It's 84. So this one, C2H3O2, is acetic acid. But the way I learned it is like this. That's why I put those both in there. Because that gives you more information about the structure of the molecule. They're exactly the same. But when you write it this way, we know that we've got this with hydrogens here. Right? Those 3 hydrogens. Then it's connected to another carbon, and one carbon has this and the other carbon has that. That's why we write it that way. That means this is the acidic hydrogen. That's the one that dissociates right there. You don't have to know that. I just put it in there for fun. If you know this one, good to go. But in some older literature, right, maybe on an old bottle somewhere, you may see it written this way. And phosphorus trichloride is a no-brainer. Those are both nonmetals. We name it type 3 compound. Okay. Which of the following statements is a consequence of the law of definite proportions? Remember, definite proportions is no matter where the compound comes from, the same ratio by mass of elements for any of those compounds, once we identify that. So, now first one is, first one's talking about isotopes. Mass of oxygen combined with a fixed mass of nitrogen in each of the binary nitrogen. No, that's multiple proportions, B. C, the atomic mass of all the elements in a periodic table have fixed values. Nope, sorry. The percent lead by mass in a compound galena is the same for all pure samples obtained from any source. That's it. That's definite proportions. Multiple proportions, looks like we're using the same series. Multiple proportions would be the mass of oxygen that is combined with a fixed mass of nitrogen in each binary nitrogen oxides can be expressed as a ratio of small whole numbers. That's multiple proportions. 88. Which of the following elements does not have a symbol taken from the Latin name for the element or one of its compounds? All right, so which one is derived from its English name? It's similar to its English name. Right? Iron is Fe, copper is Cu, sodium is Na, potassium is K. Titanium is Ti. That's it. Which of the following ions, number 90, is not likely to form from the appropriate atom? Okay, start from the bottom. Sodium is an alkali metal. They're always +1 charge. That's a good one. Titanium 4+, you'd have to look that one up in your periodic table and see is that a possibility for titanium? So you look it up, and you know, up in, for this particular table, upper right hand of each of the boxes are the possible ions. And titanium, sure enough, +4 is there. So that's valid. Magnesium, alkaline earth, 2+ charge. That's it. Arsenic, 3-. It's a member of the phosphorus family, and it's a -3. What you'll notice is that as you move from right to left, halogens are -1, And then you move next to them is the chalcogens, the oxygen group. Those are -2. Next to those are the nitrogen group, pnictogens. Those are -3 all the way down, as long as they're in ionic compounds. So that arsenic is in that group with phosphorus. It is 3- charge. That's true. Carbon, likely to form an appropriate atom? No. Carbon's not going to form that plus. 4+ under extreme conditions maybe, but it's the best answer for not likely to form. Okay, 91. How many protons, neutrons, electrons in that order, P, N, E, are present in the anion formed by one atom of I-125? Okay, so iodine, we look it up, 53. That's 53 protons. So protons, 53. Is that the first one? Yeah. Next one is neutrons. So that would be 72 neutrons. And electrons. The anion formed from one atom. That's a halogen. So it's going to have one extra electron. There you go. So that would be D, 53, 72, and 54. That could slip right by you if you don't see that anion. Right? Anions are negative, cations are positive. All right. Is this ever going to end? How much time do I have left? All right. Which of the following atoms, isotopes, or ions contain 23 protons? I have to clear myself out here. 18 electrons and 27 neutrons. All right. 23 protons. See, let's look it up. What's 23 protons? 23 protons is vanadium. So it's either C or E. Okay. Vanadium's a metal. It's more likely to be a cation. So I would say C would be your best bet. Like if you're in a hurry like I am now. 95. Which of the following compounds is incorrectly named? I'm going to let you do that one on your own. Right, because we need to get on.